In this video, we're going to cover section 11.3 on the preparation and reactions of carboxylic acids. And as you can see in this table, there are a variety of ways in which we can prepare carboxylic acids. But we've only looked at one method so far, and that is we've looked at how we can oxidize primary alcohols. So if we take a primary alcohol in the presence of chromic acid, which can be prepared from sodium dichromate, sulfuric acid, and water, we will oxidize the alcohol to the carboxylic acid. And recall how this primary alcohol, the first step of oxidation, does lead to the formation of an aldehyde, but that we can't isolate the aldehyde under these strong oxidizing conditions, and so our final product is in fact the carboxylic acid. Now let's look at another method that we can use to make a carboxylic acid. So recall one of the carbon nucleophiles, the Grignard reagent, here. And we said that, in fact, when we look at a Grignard reagent, this carbon part of the species really is acting like a carbanion, that this bond is highly polarized. In fact, we will often indicate this as being ionic in many ways, which we have a full negative charge on the carbon center and a full positive charge on the magnesium center. So if we treat a Grignard reagent with carbon dioxide, we can see the net result is the formation of a carboxylate. So the carbon nucleophile, the carbanion from the Grignard reagent, organolithiums will work in a similar fashion. We will have nucleophilic attack onto the central carbon of CO2, the only carbon in CO2, and that generates a carboxylate. In a second step, that carboxylate is quenched or undergoes a proton transfer with a acid wash. So we can use a dilute acid, H3O+, being shown here, and that can be the proton source to form your final carboxylic acid. So we can use Grignard reagents. Again, we can also use organolithiums. If we react them first with carbon dioxide, and then as a second subsequent step, introduce a dilute acid, we will convert the carboxylate that's formed initially into the final carboxylic acid. So as you can see, we could go back one step to the alkyl halide as a starting point for this particular synthesis. So if we start with really any alkyl halide in the presence of magnesium, and what's shown here wasn't shown in previous slides, but this is diethyl ether. This is a solvent that we typically run Grignard reagents in, often abbreviated as ET subscript 2O, but diethyl ether, commonly known as just ether, it's a dry solvent, and so it can be used in the formation of a Grignard reagent, as shown. And then if we carry out this two-step syntheses, first introducing CO2, and then doing our acid wash, what we've done in effect is we've increased the amount of carbon in our final product relative to that of our starting material. So what's highlighted in red here is that single carbon from CO2, and that now is found in our target molecule. So similar to alkylation and similar to the use of other carbon nucleophiles, we are basically increasing the amount of carbon in our final compound relative to the initial reactant. Now let's look at a couple methods for reacting with carboxylic acids. So because carboxylic acids are acidic and contain mildly acidic protons, if we treat those with a strong base, such as sodium hydroxide, we will deprotonate the carboxylic acid to give us the carboxylate salt. And so if we wish to prepare a carboxylate salt, this is a convenient, easy method, basically an acid-base reaction between the stronger base and the carboxylic acid. Now, if we wish to reduce the carboxylic acid, we've seen previously that with lithium aluminum hydride, we will reduce to the primary alcohol. And the last step in that mechanism, if you recall, is a acid wash or a proton transfer from some protic solvent. Now, in the upcoming videos, we'll look at a few additional reactions of carboxylic acids. But for now, if you have any questions regarding the preparation of carboxylic acids or these two specific reactions, by all means, send me an email. Thank you.